we have the hypothetical situation. We have two runners that ran in a track meet. And remember, now this is 14:04:05, okay. First person ran in a 400-meter race. The mean time of the people that ran the race was 53 seconds. The standard deviation was 2 seconds. And the time of this person was 52 seconds. Another person ran 100 meters, where the mean time was 10.6 seconds, standard deviation 0.3 seconds. And their time was 10.5 seconds. The situation I describe is they're kind of ragging at each other after the meet. They both did pretty well. They beat the average time, but nobody won their race. And you know, they're saying, "Oh, man, I ran better than you did." I said, "No, I ran better than you did. I felt pretty good today." And then they get into a little give and take, friendly, ragging at each other a little bit. Well, the question is, who really ran better? Turns out it's pretty close. So close that we don't really have confidence that we can say who ran better. But somebody can mathematically come out of here with bragging rights. Okay, so what do we do? How do we compare the performance of this runner with the performance of this runner? Well, at this stage, I said, okay, draw normal curves. Draw a normal curve for each race and show me where each runner is in that race. Well, fortunately, people did pretty well with that, but let's be sure. If we draw a normal curve with -2, -1, 0, 1, and 2, 60% of the middle height here at 1, about 1/8 of the middle height here at 2. We get those characteristics, so we get a pretty good representative normal curve. And that 60%, just a little over half. Here's half. So here's 60%. We come over, we get 1. We come over, we get 1. It works out pretty well. 1/8, take half, half, and half of that, there's 1/8. And that's about where the curve is when we get out to z equals -2 or 2. And of course, these are z values, and we're going to call these x values. Now, people did still have some trouble putting in the x values. We want to be sure we understand what all this means. 0 is the middle. That's the mean. That's the average. That's the mean of our distribution, and the mean is 53 seconds. So at z equals 0, we have 53 seconds. Standard deviation is 2 seconds. Well, every whole z number is a standard deviation. So between here and here is a standard deviation. A standard deviation is 2 seconds. So between here and here is going to be 2 seconds. So on our x scale, which measures the seconds, we're going to have 53 here, and 2 more than that, which is 55 here. And 2 more than that, which is 57 over here at z equals 2. And going to the left, of course, we're going in the negative direction, so it'll be 2 x units less, so we're going to get 51, then 2 x units less than that is 49. Now that is what we do every time we're given a mean and a standard deviation. We draw our z curve and try to draw it accurately so we have a pretty good basis for estimating and testing our final result. In case we made a mistake, we should have an accurate enough picture that we can judge whether that mistake was in our picture or in our calculation. Okay. Anyhow, we do this, and we do this for the other race, which has a mean of 10.6. The 10.6 goes here. Standard deviation of 0.3 seconds, so we go from here to here has to be 0.3 seconds. That gets us from 10.6 to 10.9. And another 0.3 seconds gives us 11.2. Going to the left, we get 10.3 and 10.0. Incidentally, these are pretty fast races, way faster than anything I'd ever have done in my so-called prime. Okay, so, there we have it. We have two pretty fast races. These would be decent times for a college level competition at some level. And they might be fairly typical standard deviations, although I think maybe this and, yeah, it might be typical. Okay, plausible anyway. Okay, well, so it's a plausible situation. Now, what do we do next? Okay, we used all our information. Have we drawn a picture? We've drawn a picture that represents each race, haven't we? But we haven't yet included the performance of these two individuals. Well, that's pretty easy. This individual had a time of 52 seconds, so 52 has to go onto this graph. This person had a time of 10.5 seconds, that has to go on this graph. Where's 52 on this graph? 52 is one of your times, that's what our x values are. So, well, 52 is halfway between 51 and 53. Doesn't take a whole lot to see that, so you're going to draw the 52 right here halfway between z equals -1 and z equals 0. And you're going to probably conclude, without having to use a formula or do anything, except just notice it, if this is halfway between here and here, then z has to be -0.5, right? So we've got our z. Okay? Now down here, well, time was 10.5, and that goes between 10.3 and 10.6, but it's going to be closer to 10.6. So it's going to be a little on this side of halfway. That alone allows us to judge who did better. But it's going to be such a small difference that we're not going to have any real confidence in it, okay? But one person is going to get the reg on the other a little more because of our analysis. And of course, the other person's going to do what people do when science tells them something that they don't like. They're going to, I don't believe that. Okay, that's just science, isn't it? Well, in this case, there might be some validity, but it would be more statistical. There's, the argument that the other person would have is there's too much uncertainty. Even these times are uncertain. A difference of a little fraction of a z value, that's nothing. We did about the same. As a matter of fact, I still think I did better than you did. Well, there could be an argument, a real valid argument for that, instead of just dismiss what you don't like. Okay. And you might think I'm talking politics, and I could be, but I'm just talking human judgment on an everyday basis. Not talking about the big issues, I'm talking about using evidence and weighing it carefully to make decisions, even in your personal life, okay? Okay, well, anyhow, here we got it. And we can pretty easily conclude that z has to be -1/3. Because, of course, between 10.3 and 10.6, you got 10.3, 10.4, 10.5, 10.6. This is on 10.5. That's 2/3 of the way from here to here, and 1/3 of the way from here to here. Okay, now I can say 10.5 lies between 10.6 and 10.3, and 1/3 of the way from 10.6 to 10.3, as you can see, just by labeling 10.3, 10.4, 10.5, 10.6. So from that, we can conclude z is -1/3. Also, we can draw this picture. Standard deviation is 0.3, so from 10.6, which is our mean, over to 10.3 is one standard deviation. That's 0.3. From our mean, which is 10.6, over to 10.5 is only 0.1. So what part of the standard, you can tell this is less than a standard deviation, it's going to be some fraction. What's the fraction? Well, 0.1 over 0.3. 0.1 over 0.3 is 1/3. If it's not already obvious to you that this is going to be 1/3, okay? 0.1 is 1/3 of 0.3 because 0.1 over 0.3 is 1/3, and that goes back to what division really means, which is something that people don't always have a good handle on. It's another thinking tool that really can be very important in making decisions and understanding things that are going on around you. So you want to work on that. Everybody can work on that. Some people need it more than others. You decide. Okay, well, anyhow, there we have it. So our z is negative 1/3. Now I got 1/3 over here because I'm just talking about what portion this distance is of this one. This obviously goes in the negative direction from the mean, so that's going to be negative 1/3, right? Okay, so now we've got a pretty good picture. I'll go on, there's more to the picture and more to our reasoning, but this is what we're going to automatically do to begin to set up this problem.